Okay, so we'll start now. So these are the important information. Okay, so we have been missing quite a few classes. Uh, I'm sorry about that. I've been involved in quite a few things. Especially last week, I shared the distinguished lecture by Professor Changzili. He was visiting our campus, and I was one of the organizers. So, so we'll continue with our discussion from the previous week. Uh, we are following David and Pozar. So, and we are here in module 4. We'll finish the module 4 today and we'll start with module 5 maybe tomorrow or by next class. We'll see about that. Okay, so in the last class, we discussed about the general solutions for TEM, TE, and TM waves, and we started with the discussion with parallel plate waveguides. So we'll quickly discuss whatever we covered in the last class. So we all remember the Maxwell's equation. So these are the curl equations from Maxwell's equation, and we have this particular dependence in the z direction. And if we try to open these curl over here, we can express these two equations in form of these six equations. So Ex, Ey, Ez, and all. So okay, Hx, Hy, Hz, Ex, Ey, Ez on the right hand side, and then can be equated to the x component, y component, and the z component. And what we can do is we can reduce the sixth equation into four. If we since there are six unknowns over here, we can express the four unknowns in terms of the other two unknowns. So Ez and Hz are on the right hand side, and we are expressing Hx, Hy, Ex, Ey in terms of Ez and Hz. So this is one thing, one simplification that we'll use for TE and TM formulation. For the TEM case, this particular thing does not work because TEM case says that we have Ez and Hz equals 0, and this implies that Hx, Hy, Ex, and Ey all will be 0. So we will discard this particular simplification for TEM case, and we'll just will return back to the six equations. Now over here we can put Ez and Hz equal to 0, and then we'll get some sort of equations. So what we can start is we choose these two equations where we have Hx, Ex, Ey, Hy, Ez, and Nz. So these two equations we are choosing, and we are using them to so yeah, we by using by comparing this, we can we know that Ez and Hz are equal to 0. So these terms vanish, and we can then simplify to get this equation over here. And then solving it, we get the value of beta, which is equal to k over here for the TM case. And we can define this cutoff wave number again. And the Helmholtz wave equation for only Ex is given by this expression over here. Now, one thing that we know that we have this particular dependence over here. So we can just evaluate dEx by dz square for Ex, which turns out to be minus beta square Ex, which is equals to minus k square Ex. So we just found out beta equal to k, so we can substitute that, and we are seeing that this particular expression over here is equal to minus k square Ex. So this term is equals to this term. So they cancel out each other, and the final reduced Helmholtz wave equation will look something like this. So this is the equation that we are trying to solve for TEM case. And again, since all this formulation was done for Ex, and similar thing can be done for Ey as well. Okay, so we have got this equation over here, and a similar thing can be done for Ey as well. Now, one useful form that Pozar has introduced is that we can express the electric field and the magnetic field in terms of the z the z coordinate, the field in the z direction, and everything else using this form over here. The E bar and H bar are all the electric field components apart from the Z direction. And this turns out to be useful in some cases. So just remember this. This form indicates this thing. Okay. Now what we can do is we can express the Laplacian of the non-Z dependent term over here. So this does not have any Z. This does not have the Z direction. So we can write the Laplacian. So the Laplacian is given by del t square equals to dou square by dou x square plus dou square by dou y square. So this is the Laplacian operator. So if you put this Laplacian back into these two equations over here, we'll get this particular equation over. Okay, so okay, so a lot of substitution is going on. Need not worry. If you just try to follow these steps, you will get it. So we are just trying, we're just simplifying the notations to so that we can save some space over here by writing the expression. So this will get too lengthy if you try to write it for ex, ey, hx, hy, and so we are expressing this as a Laplacian. And knowing that this can be expressed as a Laplacian, we can directly give solution as well. So now again, so we are just remember that we are doing general solutions. So not a lot of things will be connected. So they will get discrete solutions for a number of things. So now again, we are expressing the electric field in terms of the gradient of a scalar potential. So we are introducing this scalar potential term over here, and we can express the electric field as a gradient of the scalar potential term over here. And now this gradient term is given by this expression over here. So this is the operator that is working on the scalar potential. Now, using our previous knowledge, we know that the curl of electric field. So if you substitute the this particular expression over here, so we know this from the previous slides. So if you substitute this expression, so it turns out that this particular thing is zero. So this is something some observation over here. And now what we do is we substitute the electric field term. So we know that the displacement field can be expressed as epsilon times electric field. And now if you take divergence of sorry, curl of divergence curl. Okay, you take the dot product with curl. Okay, I'm just missing out the term. This is divergence, curl, and gradient. Okay, so we take the divergence of the this displacement current, and it can be again you can substitute this electric field term over here. You find out that this is again equal to zero. Yeah, so this is again another observation. So we can find if you substitute this over here, we finally achieve this particular result. So we see that the Laplacian of the scalar potential is again equal to zero. So this was the term that we are trying to achieve over here. So we have got the scalar potential that it's del square and this Laplacian is equal to zero. Now again, this is one known solution over here, and again, so since we are considering two conductors for this particular case, what the other two unknowns that we can find out are the voltage and the current on these two conductors. So the voltage difference between the two conductors can be given by V12, which can be written as the difference between the scalar potential of the two conductors. So this phi 1, phi 2 are like some absolute are relative to infinity, and the difference can give the potential difference between the two conductors, and it can be also expressed as the integral of the electric field between them, and the current can be expressed as current can be given by the Ampere's law. So these again, so we have got the voltage and current. We have got we can find out the scalar potentials, and we can find out the electric field and the magnetic field from the previous slide. So these are some general solutions for TEM waves, and some important observations are the TEM waves can exist when we have two or more conductors. A single conductor cannot support TEM waves, and so these results are also saying the similar things. Now, other important things are like finding the impedance. So the impedance is given as the ratio of the electric field to the magnetic field. So Ex by Hy will give you omega mu by beta, which can again you can simplify and write is write it as eta. And similarly, you can also use minus Ey by Hx, and you will again get the same thing. And combining the above results, like yeah, the previous results, we can express the magnetic field in terms of the electric field and the intrinsic impedance. So this formula is quite widely used. Uh, just in place of this, we are usually expressing eta over here. Now for the TE waves, what we over here we can use the four expressions that we got from the Maxwell's equation, where we are expressing the Hx, Hy, Ex, and Ey in terms of Ez and Hz. And for the TE case, we know that the Ez will be equal to 0 and Hz will not be equal to 0. So we'll substitute Ez equal to 0 in these terms, and we finally get the expression for Hx, Hy, Ex, and Ey in terms of Hz only. And again, using the Helmholtz wave equation for this particular case over here, and we know that the Z field can be expressed uh, as a function of small h z, which is a function of x and y, and we know that the z dependence is given by e power minus j beta term. So will again reduce this to we will reduce this to two-dimensional for Hz, and this is the equation that we are trying to solve over here. This will solve this separately and then just multiply this term over here. Okay, so yeah, so now we have this equation over here, and this to solve this equations, what we need to do is we have to first analyze the boundary conditions, and then using the boundary conditions, we'll get the unknowns, and then using that we can solve these equations. So this is as far as we go, and this will be solved only when you know the boundary conditions, and that will be known if you know the geometry of the space where we are trying to solve the equations. And again, once you have found out the electric field and the magnetic field, you can give the wave impedance in terms of this particular ratio. Now for the TM wave again, in the TM wave case, so we have Ez not equal to 0 and Hz equals to 0. So we'll just substitute Hz equal to 0 in these four equations, and we can get the electric field and the magnetic fields in term of Ez. And again, the Helmholtz equation is given over here, and we can express the electric field in terms of small e z, which has dependence on x and y, and we already know the z dependencies of some this form e power minus j beta z. So we can reduce this particular equation into a two-dimensional wave equation, only having x and y, and yeah, and kc is given by this expression over here. So once we have the this equation, we again will need the knowledge of the boundary conditions for the geometry, and then we can solve these equations to get the unknowns. And once we have the unknowns, that is the electric field and the magnetic field, we can find out the wave impedance. So that's what this TEM, TM, and TEK, all these modes were about. Now, also in the last class we saw some derivations about the attenuation due to dielectric loss. So attenuation due to we can describe the attenuation in this particular form over here, where alpha d is the due to the dielectric loss, and alpha c is due to the conductor loss. So usually this alpha c is very low because we are using good conductors, and alpha d is also very less mostly. But again, if you are considering their effects, then we can express by this expression over here. So you can refer to Pozza. So as I expressed in the last class, you can this perturbation method is given in Pozza in section 2.7, how to find out the attenuation constant. But will not dwell on this. So we can express the propagation const the your propagation constant, and given by this expression over here, which can be again, this looks very complicated. Need not worry. so yeah, this is how we express. So just in case if if you're given a problem to solve, just remember these. You can remember this formula. So this is not very complex. I think okay. There's a question. What is the significance of wave impedance? It is same as electrical. It's same as electrical impedance. No, they are two different quantities. I think I have read. We discussed this in the last class. So let me just see. I have noted it down. Okay. So the wave impedance is like the wave impedance is specific to a wave. So it is the ratio of the electric field and the magnetic field. Okay, and the electrical impedance is usually the electrical impedance is the characteristics of the geometry or the structure in which the wave will propagate. So they are two different quantities. Okay, and also ZTM is same as ZT. Does this have any significance? ZTM is same as ZT. Let me see. Beta eta by k, and this is okay. ZTM is not same as ZT. You can this is k eta by beta, and this is beta eta by k, and this beta and k need not be equal in all cases. For TEM case, beta and k will be equal, but in other cases they will not be equal. And yeah, and ZTM, okay, as you asked for the first question, so wave impedance is specific to the wave, and the electrical impedance is specific to the structure in which the wave will propagate. So the electrical impedance, like the wave impedance, can depend on, yeah, the wave impedance will be different for even different frequencies as well. But the electrical impedance that is being offered will remain same. That will depend on the structure, the material on which it was built. I think I skipped some things. Okay, okay, we were over here. So this is how we express the complex propagation constant. And yeah, what we are doing is we are trying to again use the Taylor's expansion for this particular expression over here. So using this formula, we are just trying to solve whatever is there in the under root part. And so you can follow these steps. So it will eventually lead to a result looking like this. And again, so this particular part is the loss due to the dielectric, uh, the attenuation constant due to the dielectric. And for the TM case, what we can do is you can just put beta equal to k and stay c this beta equal to k over here, and for the TM case, the loss due to the attenuation constant due to the dielectric will reduce to something like this. So this is not very important right now, and mostly we will consider very low loss due to the dielectric. So need not worry, but yeah, knowing this is good. In last class, we also started with the parallel plate waveguide. So this is how the parallel plate waveguide looks. It has two conductors, and for our simplification of the geometry, so that we can solve the uh, Maxwell's equation over here, we are just considering that it is semi-infinite. That is, we know one end, and the other end is somewhere in the infinity. And the separation between these two plates is d, and the material inside the waveguide is epsilon, and the permittivity is epsilon, and the permeability is mu, and its width is w. So this is how we are defining the geometry of the parallel plate waveguide. So as the name suggests, it has two parallel plates, and that's it. So the wave will propagate within this dielectric field over here between these two waveguides, between these two parallel plates. Okay. So in the previous slides, we defined the Laplacian of the scalar potential equals 0, and we will now provide boundary conditions to this solution that we had got in the general solutions for TM modes. So So the scalar potential. So yeah, just a second. So our scalar potential, this Laplacian is equals 0, and this is confined for this region over here. X confined between 0 and W, and Y confined between 0 and D. Now we are assuming that the bottom plate is ground and it is at zero potential, and the top plate is at V naught. So we can define these boundary conditions as x comma 0, the phi at x comma 0 is 0, and phi at x comma d is V naught. And we know because there is no variation in the x direction. So in this direction there is no variation uh, for phi. We can give this particular solution over here. So need not stress, this is something we have borrowed from math people. So this is how the solution looks like for the Laplacian. And we now know the boundary conditions, so we just substitute, we just use these values to calculate the value of a and b, and the final solution looks something like this: v naught pi by d. And now we can easily calculate the electric field, which is given by the negative gradient of the scalar potential, and this turns out to be minus y v naught by d. So yeah, this was fairly simple. So we did some math previously to get the Laplacian form of the scalar potential, and now once we had the geometry with us, we just substituted the boundary conditions, and then solved. Also gave the solution for this particular equation over here, and found out the electric field as well. Now we already know the electric field. Okay, so yeah, we have done till here. Now we have this electric field value over here. We just multiply it with the z dependence. So we then we get the final electric field expression. And using the popular formula, we just take the cross product for the direction of propagation of the electric field. We get the magnetic field as well. So this is the solution for the magnetic field. So that's it. This is how we find out the electric field and the magnetic field for parallel plate waveguide for the TEM mode. And we can now find out the voltage and current as well. So for the voltage, we just integrate over y from 0 to d ey. So and doing that will lead us to this particular solution over here, V naught. So our voltage will have some this particular constant times the again the z dependence that we have in the electric field as well. Now and the current can be found out by the Ampere's law that we already saw. So again, doing the integration and everything will end up with something looking like this. So I'm skipping this maths over here. You can try it by your hand. So anyway, speaking this out won't help too much. Maybe try it yourself, and if you find any trouble over here, please let me know. We can then discuss this step by step. So voltage and current can be found out with the electric field and the magnetic field, and the characteristics impedance of this particular structure can be given now by the voltage and the ratio of the voltage and the current. So eta d by w. So we can see that this particular impedance is dependent only on the geometry and the material parameters. And we already know that the phase velocity can be given by omega by beta. So this is I think this is all about TEM mode that we and this is all we covered in the last class. Maybe I'll take a pause over here. We have briefly discussed what we covered in the last class. If you have any doubts, you can ask now, or we'll proceed with whatever we have planned for today. That is DE mode and TM mode, and then rectangular waveguides.
Can you once again explain what is the semi-infinite plane? And secondly, the fringing effect at the ends along the x-axis, how are they ignored?
Okay, so I'll first answer the second question, the fringing thing. So we are ignoring the fringing thing over here. This particular formulation is ignoring the fringing effects, and hence because if you include fringing effects, it will get more complicated at the corners. And this particular course is for like a beginner's course, so we won't take that into account. And the first question is semi-infinite is just means that yeah, maybe I can use a pen over here. So this is a very like silly thing. So we are just considering that this particular waveguide does not end over here. It goes to in somewhere in the infinity, so that we are not terminating it over here. That's it. So
Okay,
that
so
that's an
lengthwise,
assumption. Yeah, this length in the z direction, we are like assuming that it goes somewhere far, that it does not affect our calculation. So it does not have, I don't think it has any immediate effects, but that is something which is usually considered.
okay.
Okay, so we'll start with what we have planned for today. So we have covered the TEM mode and we have seen the general some derivations. Now we'll use the same theory that we have covered before, and on similar lines we'll solve for the TEM mode as well. Now for the TM mode, we know that the HZ will be 0 and we will have non-zero EZ field. So and this is something we have already seen. So the small EZ is used for the function for the electric field, which shows the dependence of X and Y components only. And we already know the Z dependence is of something of the form e power minus j beta Z. So we are trying to solve this, and now okay. Um, we were trying to find the EZ field now, and the EZ field satisfies the pressure. Just give me a second. We're considering the variation in the x direction as 0. And is that hmm, just give me a second. I think I missed something over here.
Hello, your mic is on mute, Anand. Hello.
Yeah. Thank you. Okay, I forgot that I was on mute. Okay, so what we are trying to do is we are trying to solve we have now reduced this equation, this 2D equation to this particular form over here. And like this is an assumption that we're taking. I think I was on mute when I told that I'll get back to this, like why we are doing this. This like it's not striking me why this assumption is there. If you already know this, you can share it with the class. Others, I'll come back to this in the next class. During the when we do a recap, I'll tell why this was there. Meanwhile, we'll continue with like we'll consider this and solve the wave equation. So I'm not taking any stress. Neither should you. Let's try to solve the equation. So we have reduced the two-dimensional equation to now this one-dimensional equation. And for this particular this differential equation, this we have the general solution given by Ez in terms of a sine kcy and b cos kcy. So this is the solution for this expression over here. And yeah, so this is something which is taught in the graduate level mathematics. So you can refer to any partial differential equation chapter from your math textbook. And now we are subjecting this solution to the boundary conditions. So we have the electric fields at the plates equals to zero, and by using this by using the boundary conditions, we get that this coefficient b over here is equals to 0, and the kc d is equals to n pi. So we can define kc equals to n pi by d. Uh, Now we have got the unknowns in this equation over here, and yeah, using that we can uh, we also observe that this particular kc is now constrained to discrete values. So yeah, that is one observation, and now we can give the propagation constant as again substitute the kc values, and this is our propagation constant. So so we started with the set of equations, and we reduced this 2D to this 1D equation over here, and the solution to it was given by this form, and using the boundary conditions we found the kc values, and using the kc this expression that we already had and the value of kc, we have defined the propagation constant. And now we are using this particular the solution that we had. We are like involving this with the electric field form that we had already. So we'll substitute this back, and the final electric field expression that we have is given over here. So this is what we achieve. So the electric field is now defined, and yeah. Now, once we have the EZ over here, we can find out the other electric and magnetic field values, but just by performing the differential, taking the derivative in terms of y or z, the partial derivative, and this is what comes out. So we have the hx, ey, and ex and hy equals to 0. So things to observe that for n equals to 0, if you substitute n equal to 0 over here, this will make beta equals to k, and Ez will also turn out to be 0. So, and Ey and Hx fields are constant in Ay, and hence the Tm0 mode is actually identical to Tem. So if we make the n equal to 0, this thing we'll have the Hx and Ey as non-zero, but Ez will be equal to 0, and we will again reduce the Tm0, like the Tm will reduce the Tm mode to Tem mode. So Tm0 mode is actually a Tem mode. And for any other n greater than 0, this will be different. So in that case, we will have Ez non-zero, and we'll have Hx and Ey terms as well. And for every value of n, we will refer to that particular mode as Tm. Like for n equal to 1, this will be Tm1 mode. This, again, for n equal to 2, this will be Tm2 mode. Okay. So again, for beta also, we have similar observations that beta is real only when we have k greater than kc. This is the cutoff wave number, right? So so and so hence the wave propagation will only happen when this beta is real, that is k is greater than greater than kc. And for this we can define a cutoff frequency when that particular case uh, when k is equal to kc. So all the propagation will happen when beta is when this particular beta is real. And this is how we are defining the cutoff frequency. And just substitute, just make k equal to kc, and we will end up with something looking like this. And we have this n over here, and this n defines the cutoff frequency for that particular mode. So for every mode, we will have one particular cutoff frequency. Okay, so we can take one example. For example, if we take t TM1 mode. For the TM1 mode, this cutoff frequency will turn out to be 1 by 2d root under mu epsilon. So this is the cutoff frequency for TM1 mode. Again, we can substitute n equal to 2 and get the cutoff frequency for the higher mode. So this is yeah, something like on this line can be asked in exams as well. So you can remember this particular formula. And one important thing is this frequency is below the cutoff frequency of a given mode. The propagation constant is purely imaginary. Okay, so if this particular k is less than kc, this will turn out to be imaginary, and the beta will be imaginary, and hence for those cases, those modes like those frequencies will not propagate in the wave. They will decay as soon as they are launched in the waveguide. They will decay, and so these waves are this particular modes are called as the cutoff modes or the evanescent modes. So we must have already heard about the evanescent waves. Similarly, these are the evanescent modes. So uh, if k is get less than kc for that particular mode, those modes will not propagate. Now we can find out the wave impedance as well. Again, taking the ratio of the electric and the magnetic field. This will turn out to be beta eta by k. And again, from the previous observations, we have seen that this particular the wave impedance will be real when the frequency which we are considering is greater than the cutoff frequency, but it will be imaginary if it is less than the cutoff frequency. And hence imaginary impedance means um, will offer will not support the wave propagation. The phase velocity again is given by omega by beta, same over here. So yeah, and the guided wavelength now is defined as 2 pi by beta. So this is something different. So this We'll discuss this in coming slides. So guided wavelength is the wavelength of between the two phase fronts. Okay, there's a question: what is the significance of TM0, TM1, TM2, etc.? So these are different modes, the way in which the wave will propagate. So it can be like giving it a physical meaning, I don't have a very good answer for this, but at the last slide of today's presentation has some depiction of how these modes look like while propagating in the waveguides. So maybe we can discuss some things over there. So you'll have to hold on to like some more discussions, and then we'll cover rectangular waveguides after this, and after that we'll see at the how the uh, electric fields and magnetic fields look like inside the waveguides when they are propagating under for different modes.
Sure, thanks. One more question here. When you say real impedance and imaginary impedance, is it same as electrical terminologies where it is resistive or lossy and capacitive or inductive, something like that?
um uh, mm, ac- I cannot comment it on right now, but it should be different because over there, if it is imaginary, then you have positive and negative, and then you define the it as inductance or capacitance. But
Mm.
I'm not sure whether if when it is imaginary over here, then we call it inductive or capacitive, because we are taking the ratios of the electric and magnetic fields. So I'll
Mm.
have to look into what exactly pure imaginary means, but it sure does not support the propagation of the wave in that case.
Okay.
So over here, what will happen is that the waves will decay in so it will become like what we are trying to say is that the impedance is imaginary, and hence the waves will not propagate in that medium.
Okay, got it.
So I'll again look into this, because it's a very good question. I've never thought it like what happens if this is imaginary, like what happens if it is positive or negative or some things like that. Okay. Again, we have already defined a cutoff frequencies. On similar lines, we can define cutoff wavelength again. You can either talk in terms of wavelengths or frequencies. So does not really add much to it, but yeah, like the problems can be given to you in any form. We should be ready. So we have a cutoff frequency, we have a cutoff wavelength, and okay. So now coming to the TE modes, we'll do these same formulation for the what we did for TM mode and for the TE modes as well. So we reduce the 2D this Helmholtz equation to this 1D form, and again the general solution is given by similar expression. And since we know the geometry, we have the boundary conditions known to us. So using the boundary conditions again, we can express the electric field given. Okay, so one step that is added over here is that we have the boundary conditions for the electric fields, and we have the solution for the magnetic field over here. So what we do is we use one of these six equations. So which one are we using? So we have the Hz. We have the boundary condition for Ex. So we substitute Hz over here, and we calculate Ex. And once we have Ex, we substitute we calculate the Ex, and then we perform the boundary. We add we like yeah we use the boundary conditions on Ex. Now once we do that, we find out that A is equals to 0, and Kc turns out to be n pi by d. Now using this information, we can define the final solution for Hz again, which turns out to be something looking like this, so which has cost dependence over here. And once we have this Hz, we can use the Hz to find out all the other electric field and magnetic field components. So we have Ex, Hy, Ex and Hx, Ey and Hx are 0, and we have the Hz known over here. And again, the propagation constant in this case can also be defined as root over k square minus, and we have substituted the value of kc over here. And cutoff frequency and wave impedance are again defined for similarly for this case as well. So whatever we did for the TM mode, we did it for the TE mode as well. Just one thing that we had to be careful about, that we had the boundary conditions for the electric field, and we had the general solution for the magnetic field. Okay, so before that, okay, I forgot that we had for parallel plate wave, we had also the how the modes look like. So maybe I'll switch to a pen. So the dashed lines are the magnetic field lines, and the continuous lines are the electric field lines. Okay, it was there already. Okay, so this is how it looks for the TM wave. So this is the first plate over here. For example, if you consider this is plus, this is minus. So the electric fields are looking something like this, and the magnetic field lines are circling around this. So this is the TM wave, how it looks when it is propagating through this wave, right? So we are looking from this side. So I'm trying to draw an eye over here. Yeah, so we are looking from this direction. Okay, so and this is how the TEM case looks like. Now TM1. Okay, so this is the TM1. Now for TM1, what we have is we have the electric field varying some in a different form. Okay, so it should be yeah, the electric field varies in this form. So this is your origin. You have one maximum over here and one maximum over here. So the this part has zero potential, and we have electric fields in this direction. There is some lag with my cursor, and again the magnetic. Okay, in this case, the magnetic field lines were all both in the same direction. Okay, but in this case, you can see they are in the opposite direction. So this is how a TM1 wave propagation will look like. And for the T1 case, you have the electric field lines in this direction, which is totally different as compared to the previous cases. And the magnetic field lines are in this direction. The magnetic field. So, so physically, they refer to different types of the different arrangements of the electric and magnetic fields. Aishwarya, maybe if you were able to follow this, if you do you have any follow-up questions on this?
No, not at the moment.
Okay, sure. We'll move next to the rectangular waveguides. Over there, these things will again come back, and we will see some more these plots at the end of the class. So this is a summary of the different results that we calculated for TEM mode, and TE mode. So I think I skipped some parts. Like I think I have not covered this thing. So yeah. Okay, rest of the things I think we have not we've skipped alpha C. But all these results are from Podzar, and the derivations are also present there. So if you want to take a better look on the things that we skipped in the class, you can refer to textbook. But this alpha thing is not very popular in, I think, the in bachelor's colleges, BTech. It is not very popular. The rest results are very important. So if you're appearing for GATE, this will be important. Okay, now we'll start with the rectangular waveguides. So let me change to laser pointer. So up till now, we were looking at parallel plate waveguides. So it has two conductors. Now rectangular waveguide has only one conductor, and hence it will not support TEM wave propagation. Um, but rectangular waveguides are very popular, especially for military applications or scientific applications. And a lot of different devices are built using the rectangular waveguides. For example, couplers, detectors, isolators, attenuators, slotted lines. So these are different microwave devices. And the photos are also over here. For example, there is this bend over here. There is this coupler over here, Magic T. Variable attenuator. So all these are employing the use of rectangular waveguides, and hence it is important that we know about how they work. But right now, since due to the trend of miniaturization, for example, your smartphones only have this PCB and everything is integrated on that. So everything is moving towards miniaturization and integration, and hence waveguides are also now being fabricated using planar technology, using on like once we have the strip line and the microstrip lines. So they are the planar technology that have waveguides. But the mathematics is slightly more complicated for this class. So we'll just restrict ourselves to rectangular waveguides. Pozar has some discussions on them. I'll recommend you go through them. Rest need not worry. They work very similar to the parallel plate waveguides that we have seen. Okay, so I think we have covered most of the top points that I wrote over there. Yeah, so the waveguide, these rectangular waveguides find their applications in power systems, millimeter wave applications, satellite systems, and some test applications as well. So for high power systems, it is because these structures can handle high power as compared to whatever the planar technology that we are looking at. They are usually meant for low power devices. Okay, so this is the how a rectangular waveguide looks like, uh, a very simple diagram. So we have this metal sheet which is wrapped around, and in the inside we have some dielectric which has permittivity as epsilon and permeability as mu, and this dimension in the y direction is it is b, and in the dimension in the x direction is a, and the usual trend is that a is usually greater than b. So that is how we will orient our waveguide for the rest of this course. And we already know that since it is a single conductor device, it will not have TEM mode. So we will start with the TE mode, and the TEM mode I will leave it as an assignment. So it will be very similar to what we do for the TE modes. Okay, so for the T waveguide mode, we have the 2D uh, wave equation that must be satisfied. So, and this does not have the dz component over here, because the z variation is in terms of e power minus j beta z. So we'll just first solve for this and then multiply the z dependence over here. And this okay, so you can see over here the magnetic field hz uh, can be given as this hz term over here, and the e power minus j beta z, the z dependence term, and the cutoff wave number is expressed like this. Now to solve this particular partial differential equation, we borrow some techniques from our math friends, and we express the solution of hz in terms of capital X, which is a function of x only, and capital Y, which is a function of y only. And we use this back into our partial differential equation. So we're assuming the solution, putting it back into the equation, and then trying to solve the partial differential equation. So if we substitute this back, this is something that we will obtain this particular equation, and now this can be solved in by using some more techniques that will take our math students help. So okay, so we have seen that this is something that we have achieved till now. The partial differential equation has been simplified to this form. Now we are defining some constants, separation constants kx and ky, and we'll put them equal to the this differential terms. Okay, let me maybe I'll use a pen over here. Okay, so this particular term is now equal to kx. This particular term is equal to ky. So if you put them equal to ky, you will be able to like if you put this equal, you can multiply this y term with this term over here, and this is what we will achieve. Similarly for x as well. So this is what we do, and now once we have got the this PD for capital X in terms of x, and similarly for y, the solution for this is very simple. It is given by e cos kxx, b sin kxx. So and hz was a product of capital X and capital Y. So we multiply the solutions and perform the boundary condition, like we use the boundary conditions to evaluate the unknowns over here, a, b, c and d, and we also have the unknowns kx and ky. uh, and now the we know that the electric field on this metal like PEC will be 0. So using that information, we will try to solve this. But again, we have electric field over here and magnetic field over here. So we'll first need to find out the electric fields, the Ex and Ey. So we have these four equations that we used earlier, where the hx, hy, ex, and ey were given in term of hz. So we calculate the ex and ey terms using them. So we just substitute the hz thing over here, and the hz is actually you multiply. Okay, maybe I'll just write it over here. So we had already seen, right, the hz is equals to small hz into e power minus j beta z minus j beta z. So yeah, this, so we substitute this hz over here and then find out the ex. So the capital E that we will get will have the capital. Okay, so the capital E x that we'll get will have some things, and then it will have this e power minus j beta z. So these things which are over here is written here. So we have just removed the e power minus j beta z term, and what we have the ex and ey terms over here. Now we just directly use the boundary conditions, and using the boundary conditions, we obtain that d is equals to 0, and ky turns out to be n pi by b, and b is also equals to 0, and this is equals to m pi by a. So these are the results that we got, and then we'll substitute them back to our solution, uh, back to the magnetic field over here. So the final magnetic field solution will be given like this. So this AMN is actually the product of A and C, right? Yeah, A and C. B and D are 0, so these two terms are ignored, and we have substituted the value of kx and ky over here, m pi by a and m pi by b, and amn is actually the product of a and c. Okay, now since we have already found out the magnetic field Hz, now we can calculate the rest of the electric and magnetic field values by just using by substituting the Hz over here and finding out this derivative and multiplying with these coefficients. And it turns out that all these can be found out, and this is the full set of electric field and magnetic field values for a rectangular waveguide for TE mode. TEMN mode. And for every value of M and N, we will get a particular set of electric field and magnetic field values, and those fields will correspond to that particular mode. Now, for finding out the propagation constant, we substitute the value of Kc, which is equal, which we had seen to be equal to Kc was equals to uh, kx square plus ky square, and substituting that, we can define another cutoff frequency again for these modes as well. So beta will be real only when this k will be greater than kc, and hence we can again define a cutoff frequency where this k will be equal to kc, and as it turns out, this cutoff frequency is equals to root over m pi square by a and n pi square by b. Yeah. So this looks complicated, but yeah, need not worry. You can refer to this text to find out the value. So what I've seen is colleges usually this derivation is asked, and after this derivation only any numerical is asked. So do not stress if you can't recall the entire formula. But if you tried solving some numericals, you'll get a hang of this. What we can do is we can just find out the lowest cutoff frequency, which will for T mode, and it turns out to be since we know that A is greater than B, we're finding the T10, so where M is 1 and N equal to 0, and it turns out that this will come out to be 1 by 2A root over mu epsilon. And we call this particular frequency this is the lowest cutoff frequency that you can get with this formula, and this lowest cutoff frequency is called the dominant mode. So this is the lowest frequency that can travel in this particular waveguide. So this rectangular waveguide is actually a high pass thing, and the lowest frequency that you can send through this waveguide is dependent upon which mode you're working at. So, and this is the lowest frequency that you can send through this, which can travel in this particular waveguide. Anything lower than this will not travel. Again, so it is written in text also over here that at a given operating frequency f, only those modes having a frequency greater than the cutoff frequency will propagate. Modes with frequency less than the cutoff frequency will lead to an imaginary beta or a real alpha, meaning that all the field components will decay exponentially away from the source of excitation. So if you give a source which has a frequency less than the cutoff frequency, it will die away immediately. So it will not propagate, and we more than one mode is propagating, and then it is said to be overmoded. So if we are having, for example, if we are exciting it as T at 20 and T10 as well, so we will have more than one modes propagating in this particular waveguide, and we can call it as overmoded. Now we can define the wave impedance for this again. And again, it turns out to be k eta by beta, and again, so if beta is real, then this zt, this wave impedance will be also real, and we will have a propagating mode. And if beta is imaginary, zt will also be imaginary, and if we call it as cutoff mode because it will not support wave propagation. Now, the guide wavelength is defined as the distance between two equal phase planes along the waveguide. Okay. So this is something specific to the waveguides. We have a term called the guide wavelength, which is calculated by 2 pi by beta. And as it turns out, it is different from the wavelength of the wave inside the waveguide. So the guide wavelength and the wavelength of the wave inside that particular dielectric might not be same. Uh, and similarly, it could be greater or less, and we also define the phase velocity, and this particular phase velocity can also be greater than the velocity of the wave propagating in that particular dielectric. So yeah, so if it turns out that this comes out to be greater than speed of light, need not worry, because phase velocity can be greater than the speed of light as well. But but in the but the information is being like sent through group velocity, which is another term that we'll see in the next class, uh, and that will turn out to be less than the speed of light. So these are some important things that we covered in on the TE mode. TM mode, I'm leaving it up to you. You can try solving it. You can take help of our textbook Poza that we are following. Has all these similar formulations, and yeah. So if you are able to derive all these results for TM case, then you can be sure that you have like understood this clearly. And this is a summary of all the terms that we have like derived. So this particular table is also there in Podzar. So this is a quick cheat sheet for you if you want to recall or try to solve numericals from Podzar. Yeah, and this is what something I was like referring to when Ashwarya asked the question. Maybe I'll switch to. So the Podzar has given this really nice figure. So first we need to see which cross section we are looking at. So you can see this particular 3 over here. So 3 is actually the cross section in this particular plane. Okay. So we are cutting the waveguide in this particular plane. So 3 is over here. For the TE case, we will have the electric fields align something like this in this direction. And the magnetic field lines will be in this direction. Okay. And so this is what it looks like from the front of the waveguide. And if you take a cross section, for example, 2 is the this particular plane. We are cutting in this direction. So in 2, you will see that the electric fields are like sometimes like they have positive over here, and sometimes they will have positive. So this is how the wave will propagate. So this is if the wave is propagating in this direction. The electric field will sometimes have positive polarization on the upper plate and negative in the lower, and this will again switch to positive below and negative above. So the electric field will keep switching from uh, this direction to this direction, and the magnetic field is looking inside. So magnetic field we can see in this particular figure. Now this one is the cross section like this in this plane over here. So if you in one, if you see, you will see the magnetic field lines how they are looking like. So they are basically circling around the electric fields over here like this, and the electric field is actually like going from top to the bottom. Um, okay, so I just tried explaining the field lines in T10 case. Where you like anyone has any questions on this? If I need to explain it once again, so I'll try maybe explaining T20 and then let you maybe try to understand the rest of the figures. You can also use maybe CST or CST or HFSS or some other tools as well to get these plots. there is some issue with my pointer actually. Yes, yes. There was one more tool called okay, this is I 3 E and D. I don't know whether so the CST HFSS I3ED, I think if I recall the name correctly. So these tools can help you get these plots. Okay, I'll try maybe explaining T20 as well. So in T20, over here we had electric field variation like this. And in T20, we will have an electric field variation like this. So we have some positive values of this positive and then this negative over here. And we have positive and negative over here. And if you look closely, maybe again over here, this is the same as case of the previous case, and we have the for yeah, okay, let's if we take a look at this particular cross section, the magnetic field. So we have T20, right? So we have the electric field values varying like this. Okay, maybe I'll try drawing it over here. Something like this. And similarly, the magnetic field are also taking a circle like this. And the electric field values are now like so. Okay, I think there should have been these should have been cross, one of them at least. One of them points the electric field direction and the inside, and one of them points outside. So over here, the in this place, the electric field is going inwards, and over here they are going outwards. Okay, maybe I'll use a pointer because this pen is not working. Okay, so in this particular region over here, the electric field is going inwards, and over here they should be going outwards. And similarly, the this direction of the magnetic field lines is also changing. So this is for the T20 case, and on similar lines you can decode this. So I think maybe some over here they have given all dots over here. Some of them might be across. Maybe you can refer to a different textbook. But also doing a simple Google search will can help you understand this. Okay, maybe
What
so
is
just give me a
causing the
second.
bending of lines?
Come again.
What is causing the bending of electric field lines in T11 and onwards?
Okay. Okay. The bending of electric field lines. Hmm. So the field lines, like they
It looks like two dipoles in which it's shared here.
yeah. So the thing is, I'm not. They are bending, right? Okay. Yeah, you can consider them to have like fictitious sources, and then you can try drawing the lines. So the thing is, if you can, so this T11 you are talking about, right? This thing. Is it third figure what you're talking about?
Yes, yes.
Okay, so the electric field lines are given over here. So again, maybe I'll use a pen over here. So the electric field, it turns out to have some plot like this. Like it starts from one magnitude, crosses zero, and then comes back to some magnitude. So so the electric field lines, it is bending from this sheet to this sheet, right? So it probably means that it has a positive charge over here, like some positive over here and some negative charge accumulated on this particular sheet. So this that is why the electric field is moving from this point to this point, like something of that sort. And the magnetic field is again perpendicular to it. Maybe using a different cross section will help us gain better insight. So, okay, maybe this is two is like this side portion, right? So yeah, so the magnetic field lines are encircling the field lines, and this field lines is turning out to touch the other port. Okay, maybe let us instead of dwelling on this thing, I'll try sharing something from online. Just give me a second. If I can find a good figure for TE11 mode propagation. Okay, I could not find any good figure. Maybe next class I'll try to. Maybe next class I'll try to get some good figure for TE11. I'm not sure why. But yeah, you can also try to do these simulations using CST. You will be able to see them the animations and moving in the plane. So that will help you get the idea of how the waves are bending about inside the this waveguide.
How should we decide the mode of whether we want to see for T11? What do we need to set up?
Um, okay, so it's been some time I have used CST. But as
But
I recall, when you set up the simulation, there are some options to do that. Maybe following a YouTube tutorial shall help you. I don't recall the steps very clearly, but there are options to set up the modes. And there are certain field parameters on the left hand side, the navigation tree. You will have to pick the correct one and see. So if I find a good YouTube tutorial, I'll post it in the WhatsApp group.
more generally, what decides the n value here? Is it the geometry or is it the source? Or whether it's 10, 11, 21 or whatever.
Okay, the n value is okay. The a and b are actually decided from the geometry, and n value is the n value helps you know whether a particular source will propagate or not. like if you have a particular frequency that you want to like send through this waveguide, then you can use the cutoff frequency formula to find out whether it will in which mode it will travel. Okay, so it's not like that you this is as far as I understand, this is more of a trial and error sort of thing, where you have one particular frequency, and then you put the values of m and n inside the formula and see what is the cutoff frequency for different t and tm mode for that particular waveguide where you have the a and b values with you, and then you will be able to know that which the frequency that you are considering, which mode it will travel in which modes. Okay, if like should I try it once again to explain, or were you able to follow it?
Yes, I understood. So how I understood is using the critical frequency and the operating frequency formula, we can come down to one n, or we can first fix an n and then decide what our operating frequency should be, something like that, right?
Yes, yes. So once you have a waveguide with you, you know the A and B values, the which is the physical the parameters that you have for the waveguide, the for the aperture. So you have the A and B, and now you can put the values for M and N, and using that you will get different cutoff frequency for different modes. So you can have a chart of that, and then when you have a particular source that you want to send through the waveguide, you can, using that chart, you can find out in which modes that particular frequency will travel.
Right, right, right.
Okay, so this any more questions, because this is all that we had planned to cover, and over here we are wrapping up with module 4. Only group velocity and some dispersion topic is left, which I will include in the next module. And yeah, so in the next module we'll start with microwave network analysis. We'll start with impedance and admittance matrices. Any questions from what we covered from today or in this module? Otherwise, we can end the class for today. Okay, I guess no more questions. I'll share the slides. So I'll stop the recording now.